Hello viewers, welcome to my channel Science and Technology. In today's show, Future Friday, we're going to talk about Noon Energy, basically reversible solid oxide fuel cells. So let's dive deep into it. Now again, it's the same story. We have cheap and abundant power. You need three things for a prosperous future: cheap, abundant, and available. We got the two parts sorted. Like solar alone is like, bro, we got this. Solar and wind is like, we really got this right now, today. It's just that what we don't get is availability 24 into 7. And this creates a dynamic problem. As in, our demand is dynamic. Okay, cool. So is supply. Basically, there are two variables that are going like this, and we need to balance it out. So what we need is a buffer. The best example for this buffer is basically a dam. For example, rivers are not constant flow devices. It's not like, okay, only this much water flow. Whatever number you hear, it's like, okay, this much is the flow. That's average number. It does fluctuate. It fluctuates based on season. It fluctuates versus day and night time, and all other factors affect it. So how the heck you can have a constant electricity output based on variable load from a dam? Because the reservoir is acting a two-side buffer. It's handling the supply side, it's handling the basically water intake side also. We need something like that. Now again, we do have something like that. It's called pumped hydro. It is good, it is great, it's just slow, yani expensive to make. Basically, its upfront cost is brutal. It does work. It's one of those few things that's like, yeah, we know that it will work for 50 years. Why? We have last like things that are 50 years old that have been upgraded, repaired, and like it's just a thing. It works. It's just the physical upfront cost is brutal. Time, it does take some time. So it's just that it's not suitable. So every country and continent is working their ass off to solve this problem. And what is the requirement? What would be the checklist for that? Checklist is massive capacity. Like, we are not talking about like lithium ion battery. That's not good enough. That's like barely hundreds of megawatt hour. That's not good enough. We need gigawatt hour. And like, can't I do with lithium? No, you will bankrupt your country if you try to do that. This puppy starts at multi gigawatt hour. So you need massive capacity, as in like GWH. That should be your point. And it should be cheap. Again, otherwise we could have done that. And it should be small. And again, small does not mean small as in like lithium density level, but small as in like it should not require too much. If that basically, if we can make it small enough where you can ship it with a container ship and just like not container ship as in like the container, the standardized 40-foot container, and just like it's a thing, it just goes there, you drop it, you can isolate create island grid for a small community, shut up, take money. So basically this, but cheaper and smaller. So that's the problem aspect of it. So what's the logic that people are looking into? Well, people are looking into fuel cell mechanism simply because it's a dual part system, as in generator and fuel tank are two independent systems. For example, if you look into basically Antarctica research bases, they have generators that are big. They're not tiny generators, but they're not that big. Like, they're not 600 megawatt. They're not that. But here's the deal. Their fuel tanks are huge. They're designed to run for like 6-7 months. Between refuels, of course. So that's the whole point. That's what we are looking for, because our demand is based on location, is dependent. For example, some companies will be like, bro, we got more than solar, more than enough solar, we got more than enough wind. It's just that if we had something that can, balance load everything. And again, we do not need like hours and hours of power, just like balance load it. So you need massive generator and a small fuel tank. But some places it will be completely opposite. It's like, bro, we got more than enough solar power. It's just that we do need it to like, ride out for almost like 18 hours. Big ass fuel tank. So we need to disassociate power and energy independently. Like, can't we do that with lithium ion battery? No. No matter which supplier, vendor you are looking into, there will be a cell in your lithium ion battery. It does not matter it's a big prismatic cell or a small cylindrical cell. That cell would be your fundamental limit of kilowatt and kilowatt hour. As in, the cell will define this. You can expand it, contract it, but like you can't change too much of it. It's because, again, that's inherent limitation. It's not like this. You can't have a like, oh, I have a cell that's like, huge capacity. As in like amp power is bonkers. And how many amps I can draw from it would be like very tiny. Yeah, that you can't buy that. So kilowatt and kilowatt hour is very tightly linked in a battery system, but in a fuel system, it's independent. Tank could be disproportionately stupid. Like, you could literally be like, hey, I want to store energy from the whole summer and spend it in winter. That can be done. So that's why people are looking into fuel cell topology, or even like a vanadium battery, redox flow battery, those sort of things. Basically, wherever you can separate kilowatt and kilowatt hour. basically like hydrogen. But then why don't we do hydrogen? Well, hydrogen does not like thermodynamics. Thermodynamics is like, bro, I'm your daddy. So we have tried that from 1833 and we learned it the hard way that you can try hydrogen. Go YOLO on it. NASA tried that with Apollo, tried that with space shuttle, and then like, let's just let it go. It's just not efficient enough. No matter what you do, thermodynamically, it will rarely touch 30, 40. I'm being way too optimistic with that round trip efficiency. And for the cost and the hassle that it brings, it's just not worth it. And again, that's thermodynamics. Don't say, oh, new technology, law of physics cannot be broken. Again, 1833, that's the first time we built gas batteries. We have data, we have tried it. Only investors sell this so they can make money out of you, like Nikola truck. So fundamentally, we want something like hydrogen fuel cell, but this company figured out, what if we did that with carbon? Why? Carbon is dense. So that's the logic behind it. We want something like, hey, fuel tank, put as much as a fuel tank as you want. Power, don't need that much. Like again, even in my hometown, my current inverter, it's not huge, but my electrical consumption would be so low if my battery amp power was huge. I just can't buy it, can't afford it, can't scale it. So that's the logical problem that we are trying to solve. So how the heck this works? And this is the first time I can openly say I am genuinely confused by Matt Farrell's video. He was talking about something different. Either he messed up the patent or he genuinely did not know, which again, for channel of that caliber, I'm like, come on. So let's dive deep into it. What the hell is happening? It's a carbon monoxide fuel cell. So 800 degrees Celsius, this puppy, takes in carbon dioxide and you electrolyze it. Now, why do you need to be 800 degrees Celsius? Carbon dioxide is a spent component, meaning it has already reacted. Carbon has already married to oxygen. It's like a chill state. It's like, bro, I'm chill. So to make them divorce, you have to have heat. How much heat? 800 degrees Celsius heat. What about the membrane? Ceramic membrane. And again, oxygen cannot go through it if the membrane is not high enough temperature. For electron mobility, it does need that puppy to be 800 degree white hot. So this is what we sent to Mars. This is MOXIE. If you open up the MOXIE, this is that puppy. Now, how does it work? Now, here's the deal. Carbon dioxide is a very strong couple. So divorce is not very clean. Hydrogen oxygen is a very clean divorce. You just like, 2HO. It's a very clean. Oxygen is oxygen, hydrogen is hydrogen. Here it's not that. It's oxygen, you get oxygen, great, but you get carbon monoxide. It does not get a clean slicing. It's not like you get oxygen and you get carbon. You do not do that. You get carbon monoxide and you get oxygen. Now on Mars, dumping carbon monoxide in a carbon dioxide environment does not matter. Carbon monoxide dumping in atmosphere of Earth, not acceptable. Now what this company figured out, this does take electricity. And this can be inverted also. But again, we'll talk about that further. But how do you store carbon monoxide? You can't, it's a gas, it's inefficient. So they figured out bond-to-bond reaction. I do not know this pronunciation. I keep forgetting every time I'm trying to learn that. So trick is, you take 2 carbon monoxide and you react it. At that point in time, you achieve the unique point of crystallization, as in carbon monoxide becomes carbon, hard carbon, as in solid carbon, graphite, coal, whatever have you, and carbon dioxide. And carbon dioxide you can send back to the fuel cell for reaction, or electrolyzer in this case. So you start with an electrolyzer. Electrolyzer takes 2 things, massive amount of heat and massive amount of electricity. It splits carbon dioxide into carbon monoxide and oxygen. Oxygen you dump into the atmosphere, who cares? The carbon monoxide you sent into a tank, the charge tank. In that charge tank, you do this reaction, bond-to-bond reaction. This reaction gives you 2 components. It stores solid carbon, because again, right now you are gas. Like what is coming out of this is a gas, carbon monoxide gas. That carbon monoxide gas becomes carbon dioxide gas and carbon deposit. Carbon dioxide circulates back again. You do not want to waste it. You keep cycling it and you keep dumping oxygen abroad. So that's how you do charging. And the critical asset, this you can buy. This is something you can just pick up a phone, buy, and if you are scientifically minded enough, you can build it in home. Hard, expensive, and 800 degrees Celsius, but it is doable. It's like normal item, so to say, solid oxide fuel cell. What they have figured out, the special sauce, is the charging tank. Now this tank has the ability to absorb this, as in this reaction. Now key to this reaction is that this is exothermic and this puppy is endothermic, meaning it's not like, oh, I have to just heat it up to 800 degrees Celsius and insulate it. No, it's an endothermic reaction. It will consume heat. So you have to keep dumping electricity to heat it up, or have some other process that gives you heat. That's their special sauce. The charging tank does this reaction. This reaction creates a massive amount of heat that you feed back into power block. And this is what they have achieved, which allows them to beat efficiency of hydrogen. Hydrogen cannot recycle its heat that effectively. They figured out at this sort of temperature, it kind of is easy. It's like, oh, charging tank heats up. This needs heat. Ta-da! Again, it's not 100%, but compared to 30%, exponentially better. So that's what they are doing. You have a electrolyzer cell that you just ignite at that temperature. Once you start running the process, the charge tank generates the heat you need to keep it sustaining. You are utilizing the heat cycle. So it's far more thermodynamically efficient. So that's how you charge that puppy. Basically consume electricity and have oxygen as a byproduct and carbon, solid carbon as your charge medium, and you can basically have a carbon dioxide. Be mindful, this is a closed carbon cycle, as in carbon never leaves the system. If this puppy started with 1 ton of carbon, it will always be 1 ton of carbon. It will not digest carbon dioxide from the atmosphere, nor it will add to atmosphere. Oxygen, it come and go. Oxygen is the reactant here. But carbon remains in a closed loop. It's almost like running a hydrogen fuel cell completely encapsulated. Basically, you electrolyze it to get hydrogen and oxygen, react both hydrogen and oxygen to get basically water and electricity, and then is electrolyze it again. Closed loop. Same thing is happening here for carbon. So charging tank gives you the heat that runs the cycle far more efficiently, and voila, that's how you charge it. That's step 1. Now step 2, it's you have the power block. Now you dump hot air, as in very hot air. Why? This charge tank has solid carbon. Now solid carbon, it's not gonna react to this yet. This has to be hot carbon, and here's the deal, it cannot work on carbon, it has to work on carbon monoxide. Let that be very clear. This cell, the power block, only works on carbon monoxide. So the air goes into the charging tank. Charging tank now has oxygen, basically. That's why it's gonna take oxygen from the air. It's gonna take oxygen, it's gonna react with the charging tank carbon monoxide happens, and it goes to power block. Now here's the deal. This time the charging tank is endothermic. It's consuming heat. So you start the power block. Now once power block starts, what's happening there? It's combustion. It's not pure combustion, it's oxidation, but you get the point. It dumps heat. Now power block's waste heat is making sure the charge tank heat requirement is met. So this time, this was providing the heat. Discharging time, power block provides the heat. So this is the main source of them. It's like figuring out how the heck they coupled the heat into the system. So heat is not wasted. That's why they keep talking about like, oh, they do require like insulation, they do require industrial insulation and all that. That's the reason. They're cycling the heat. They're not throwing the heat away. So during charging, power block requires heat. During discharging, power block becomes hot. You need to cool it down. So they're like dump that heat into charging tank. And because the carbon dioxide this time is created, that carbon dioxide is being squeezed into the discharge tank. So that's why I said the carbon never leaves the system. Carbon dioxide, this time you're compressing it into a tank. What does that mean? That means it gets hot. What do you need heated? Air. So air leaches heat of this, goes into the charging tank, evaporates basically solid carbon, and voila, the cycle repeats. Heat remains in the system, you get electricity. That's why round trip efficiency can be higher than 50-60%. Again, claimed. So, and their special sauce. Be mindful, these two things are not that magical. The special magical thing is doing this process without creating graphite or basically coal. So what they have in the charging tank, that's the special. This discharge tank, which handles carbon dioxide, is just a normal high pressure steel tank for liquid carbon dioxide. That's a normal thing. Like you can just go to industrial suppliers like, hey, I need liquid carbon dioxide tank. They're like, yeah, we have this catalog, select what size you want. That's like take it and go. That's the easy part. Power block, again, more than enough company that makes it, and if you know your stuff, you can build it. And again, NASA have provided full detail of this if you want to. So that's the easy part. The hard part is charge tank. What is there inside the charge tank? Some say it's iron-based, some sponge material, some say nickel-based sponge material. I have not found precise detail about it. And again, that goes above my chemistry understanding. So what they are doing is flowing the carbon monoxide gas through it, reacting it, and somehow getting what we call fluffy nanocarbon. Because again, if they ever get in a scenario where that catalyst, so to say, it allows them to make graphite, it will block out the gas passage, the end system is throwaway. So charge tank is their special sauce. How the heck they figured out this charge tank? Either it's temperature, either it's catalyst, either it's geometry, or something is there that allows them to dump basically super duper hot carbon monoxide, and it deposits a layer of carbon, and carbon dioxide goes out, recycles into the system, and voila, you have solid carbon storage. And during the discharge process, because it's nano level, super high surface area, you flush enough air through it, that air reacts only with carbon, and voila, now you get carbon monoxide. Monoxide goes into the power block gives you the system. And again, doing the boiling part, of course, you are trying to boil goddamn carbon, is gonna take energy. The power block has a lot of waste heat. You cycle it into the system. So because the heat has a complete closed loop, this can achieve very high thermodynamic efficiency. So that's the special sauce they are doing. And this is your kilowatt, as in like if you need bonkers amount of kilowatt, like you need oomph, like a UPS, you will have big, huge blocks of this. But in most scenarios where it's like, bro, we have more than enough power, we just need to ride through the night, like you just increase the tank. Discharge tank, super cheap, high pressure stainless steel system. Charging tank, I do not know how expensive the salt inside it is, but that's their sauce, special sauce. And everything is thermodynamically working on gaseous phase. There is no liquid to translate. So thermodynamic efficiency is also higher. They do not have pumping losses of a redox flow battery. And because you are getting solid carbon deposit, the size density is like exponentially better than even lithium ion, practically speaking. Like, don't even try to compare to any other system, because again, solid carbon. So that's how they work, like, and because they're utilizing the heat, like again, imagine like a discharge tank requires massive amount of heat generation. Cool, dump that heat into the air intake stream. So that's how they are maximizing the yield. The cycle is complete, not only electrically, but also thermally. So that's the working of it. This took me a whole day to figure out. So what are the unknowns here? Well, here's the deal. We have physical data that hydrogen is wasteful because of the endothermic waste system, meaning no matter what you do, unless you figure out the heat, you're not going to do much. And again, we have tried from 1833, nothing happens. So fundamentally, it is this dealing with the same problem, so much heat generation, and again, exponentially higher temperature heat generation. But because it recycles that heat, it can do something that hydrogen cannot. But let that be okay, it cannot beat lithium in round trip efficiency, meaning if you gave 100 unit of energy to lithium ion battery packs, they will give you easily 80 plus, 85 plus, 90 if you are lucky. So that's like, shut up, take money. That's like, you do not talk about this. But hydrogen, yeah, this is 3 times better. 3 times better. Electrolyzer itself has a massive thermal penalty. Fuel cell has massive thermal properties, penalty. Both of them combined gives you enough loss that you can't just do. And by the way, I removed the step of compressing hydrogen. They do not have to worry about compressing it. So that's why this is 3x better. Fundamental on a physical level, its system is better, 3x better. And to increase the capacity, they only need high pressure CO2 tank, super cheap, take it and go. One special storage tank, I do not know what's inside it. It could be mildly expensive. I do not know. They have not told me. So that's there. But be mindful, while it's not gonna ever come close to lithium ion round trip efficiency, if it's cheap enough, which is their claim. Their whole claim is that the moment you make it bigger, let's say you try to make megawatt hour, the price per unit goes down so much that it's like, shut up, take money. Shut up, take money. Again, it will not scale down. The system is not designed to be small. I'm skeptical if you can even bring it into your house. Maybe an apartment building where you have like a giant container that is doing something like this, but it requires to be big. But it does scale up big, as in like for the size of big containers, you will have exponentially more. Like instead of where a lithium ion is barely giving you, let's just say 10 megawatt hour, this puppy will give you 100 megawatt hour, or maybe even gigawatt hour. Again, solid carbon is this material. Almost coal, like you have pure coal. And again, waste heat is being recycled. So it's not just like, oh, waste heat, nah, it's recycled. So that's their claim. But we do not know the round trip efficiency from a third party point of view, as in like somebody bought it, not experimentally, somebody bought it as a final product, and parasitics are unknown. It does require a lot of fans. So those parts are unknown. Scientifically, what they are trying to do does make sense. Again, other aspects of it is real. It's here. You can buy it. Even the special sauce, I just do not know which exact compound of special sauce they have, but I have heard of the science and paper and all. It's available. You can find those. So that's the unknown part. We do not know the parasitics. Parasitics, if let's just say if it's 50% round trip efficient, it has to be above that. But let's just say it hits 50%. Cool. Still would be cool. Because we might well, I'm like the E2S power, converting coal power plants into batteries, that only goes to 30%. So still would be useful as long as it's cheap. If it's cheap enough, shut up, take money. That's the whole essence. They do not need to be most efficient. But if they are like, hey, if you want 1 gigawatt hour of storage, there is nothing that can give you that cheaply, shut up, take money. That's the only battleground they have. Make it cheap enough for large enough scale that it justifies itself. And price delta is high enough where, like, during curtailment is happening in India now. During daytime, solar farms have to shut it down. Nobody can digest that power. At that time, they will sell you electricity for few cents. And at night, you can sell that same energy for few dollars. So scale is high enough where that even at 50%, heck, even at 30%, you can sell it. That's why people are working on coal power plants to thermal energy conversion. And it also has the secondary benefit. First, you have already built it. Second, it gives you inertia while charging. Pumped hydro gives you inertia while discharging. So that is another advantage. That allows you to have more solar added to the grid. So now you can absorb even more energy. So that's why people are seriously looking into the even with poor round trip efficiency. Grid inertia, daytime and nighttime. And again, we have the infrastructure built. It's like built there. And somebody is like, hey, what if we use the waste heat for district cooling? Ultra great. So they do not have to worry about waste heat because they are cycling it. It's just that if it's cheap enough for large enough, people will look into it. So what can we expect in the future? Well, here's the deal. Science is there. Let the bigger science is there. It's just a hell lot of a hard time trying to figure out what the hell happening. But science is there. Engineering may be able to deliver it. That's not actual RT. It could be done. Although, let that be very clear, the make or break of this technology is not round trip efficiency. It's flat out cost of the package. That's the actual sus part. Can they actually do it? Now, what is the likelihood of this working? Well, almost zero. Why? I have seen this song and dance. This exact same thing. NASA engineer, if you are old enough, you must have remembered Bloom Energy. Here's the deal. They are multi-billion-dollar company right now. They actually made solid oxide fuel cell. Wait a minute. If we have solid oxide fuel cell, why don't we use it? They had the same problem as everybody else. It's not cheap enough. That's the whole point. They made it like, I'm old enough where I remember this, whoa, this can like directly take natural gas and directly give you electricity. And they are making money right now because of the data center boom. There are a lot of random places that needed data center. They're like, hey, we don't have electricity is frustrating and it will take too long to draw. They're like, hey, do you have gas pipeline? It's like, yeah, generally they have overbuilt gas capacity. It's like, hey, just have a bank of these. They take basically natural gas, it's in CH4, voila, electricity on the other end, the end, go home. And if they are smart, they might be using waste heat for running chillers also, so that will give them double dipping. That's real. It's here. You can buy it. It's just that then why does not anybody buy it? Why my car has engines rather than solid oxide fuel cell? Yeah, it's not cheap. That was their whole point. The whole company was built around we can make it cheap because everything else that it will work and this will be that's there. It's just that they could not figure out how to make it cheap. That's the main essence. And again, he made me very angry the moment he compared it to plant. It's not a plant. You are burning carbon in a closed loop. It's not a goddamn plant. Having that carbon and water and having sugar as the output. I'm like, bro, that's just mean. Like, I get it. You think everybody is dumb, but like that rubs me the wrong way. You do not have hydrogen in your system. Do not compare it to the goddamn photosynthesis. That's like, I hate this. Like personally, it rubs me the wrong way. Like Matt Farrell, I think that's the guy who was comparing it to photosynthesis. I'm like, no, there is no hydrogen there. So again, let that be very clear. I can easily believe they can make the hardware. I can easily believe them. The engineering could be reasonable enough. Let's just say, heck, let's go YOLO. Let's say 65% round trip efficiency. Let's go YOLO on that. Question is, can they drop the cost? Let that be clear. That's the only thing that is of importance here. Can they make it cheaper? Because everything else is there. It is true that if you can store energy in solid carbon, shut up, take money. It will bitch slap any other chemistry we have. The only missing link would be grid inertia. You have to invest bonkers amount of money on bonkers inverters. But other than that, and again, we have inverters, why solar? So that's not the issue. It's just that can they do that in cheap enough? How special and spicy is their, fluffy carbon, nanocarbon and all that? I do not know. How they are achieving it, I don't know. So question is cost. Again, look into Bloom Energy. Heck, there was another company that was saying that you can have range extender in your electric vehicle without having any moving part. Why? Use steel cell. That was their solid oxide fuel cell. That's why I said, like, there are more than 10, 20 companies that sell you solid oxide fuel cell right now. Pick up a phone, give them $1 billion, they will give you that. It's just that nobody has managed to drop the price. This is like surviving because of niche case. And again, that rubbed me the wrong way. Like, I get it, like, you think everyone is dumb, but please, that just rubs me the wrong way. So again, been there, done that, had the dance. So likelihood is low. Again, not on science, on basically economic deliverability. So this was my presentation on basically this whole video that I had to make because of Matt Farrell, like, whose patent you were going over? Like, he has oxygen tank. There is no oxygen tank in this. Anyway, I hope you have liked it, learned from it. In that case, please click the like button. If you have really enjoyed it, click the hype button. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me extra disappointment. Please leave a comment because I do try to reply to all of them. Subscribe, press the bell and click free. And as always, thanks for watching.